The core objective of statistical learning is straightforward. We map observed variables to continuous future outputs, extracting a mathematical signal from random noise. The foundational architecture for this mapping is the general linear equation, y equals beta 0 plus beta 1x plus an irreducible error term, epsilon. When we plot data and draw a line of best fit through it, we are not making an arbitrary estimate. That line is governed by a strict algorithmic optimization mechanism known as ordinary least squares estimation, or OLS. The mathematical goal of OLS is to find the exact coefficient parameters, the intercept, beta 0, and the slope, beta 1, that minimize the overall error of the model. We measure this error using the residual sum of squares. We calculate the vertical distance between each data point and our predicted line, squaring those distances to expand into actual squares. The OLS algorithm shifts the line until the total square area reaches absolute zero growth. The mathematics of this optimization are infallible, but the raw data we feed into it is messy, nonlinear, and chaotic. To survive real-world data, the linear model must be structurally expanded to handle multiple variables, strictly encoded to understand categories, and ruthlessly diagnosed for invisible failures. A mathematical model is only as powerful as the structural assumptions it relies on. Those assumptions must be proven, not presumed. We can scale this mathematical architecture using a standard advertising dataset, which tracks the sales of a product against budgets allocated across 3 distinct media: TV, radio, and newspaper. Moving from a simple linear regression to a multiple linear regression structurally alters the geometry of our model. We expand the 2-dimensional axis into a 3D coordinate space, calculating a flat regression hyperplane that cuts through our data. Our goal is to isolate the unique contribution of each advertising medium to the final sales output, finding individual beta coefficients while holding all other variables constant. But before analyzing the specific effect of radio or TV, we have to ask a foundational question. Does any of this data actually predict sales? To answer this, we use the F-test, or ANOVA. The F-test evaluates the null hypothesis, which assumes that every single coefficient parameter in our model equals exactly 0. It tests the assumption that our data has no relationship to sales whatsoever. The console output provides model fit statistics. A massive F-statistic of 570 pairs with a microscopic p-value of 2.2 e-16. The null hypothesis is obliterated. The F-test proves that our multivariable model is extracting a mathematically valid signal from the noise, justifying our shift into higher dimensional complexities. Continuous numerical values like budget dollars easily map to a regression line, but reality operates in categorical states. If we want to predict credit card balances, we have to process qualitative traits. This is a 10-panel grid mapping exploratory data for a credit dataset, measuring variables like income, age, and education against card balances. Notice the variables isolated in the box plots. Gender, student status, and ethnicity are qualitative labels. They defy standard numerical plotting. To force qualitative data into a quantitative equation, we use a technique called dummy coding, converting human labels into strict binary matrices. For a 2-level variable like gender, the model designates female as a quantitative 1 and assigns male as the baseline 0. Mathematically, adding a dummy variable does not change the angle of the regression line. It shifts the baseline intercept, beta 0, up or down. The coefficient beta 1 simply becomes the average measurable difference between the 2 groups. For multi-level variables like ethnicity, the rules are rigid. A 3-level variable must be represented by exactly 2 dummy variables. If we encode all 3, we create perfect collinearity, which destroys the OLS calculation. By mathematically encoding qualitative states, we force the linear model to process the discrete categories of the real world without breaking its internal optimization. Even with dummy variables, standard linear models carry a severe limitation: the additive assumption. The math assumes that every variable operates in total isolation from the rest. We can expose the flaw in this logic with a practical contradiction. Does an increase in income affect a credit card balance identically for a working professional and an enrolled student? This chart shows income's effect on credit balance. On the left, without an interaction term, the red line for students and black line for non-students are strictly parallel. It assumes new income affects both groups at the exact same rate. We correct this by introducing an interaction effect. We multiply the two predictor variables together, generating a new beta-3 term in the equation. When we plot the data with the interaction encoded, the visualization changes. The slopes are no longer parallel, they converge. Being a student no longer just shifts the intercept point, it actively alters the angle of the income slope itself. The model can now capture synergies. One variable can act as a direct multiplier or dampener on another. Returning to our advertising data, this means we can prove whether spending heavily on a TV campaign actually makes subsequent radio ads more effective. By multiplying variables rather than just adding them, the model is equipped to capture the deeply entangled reality of the data it processes. In statistical learning, securing a high R-squared is only half the battle. If built on unchecked mathematical violations, the entire structure is completely invalid. OLS estimation relies on strict, invisible assumptions. The error terms must have a zero mean. Observations must be independent, and critically, the errors must maintain constant variance, a state known as homoscedasticity. To detect hidden failures, data scientists deploy the ultimate diagnostic tool, the residual plot. This scatter plot of jackknife residuals maps model errors against predictions. If residuals fan out into a cone, equal variance destroys confidence intervals. Notice specific rogue data points, labeled 14 and 17, pushing against the negative limits. These are high-leverage outliers. A few extreme values possess enough gravitational pull to drag the regression hyperplane off its true axis. Without rigorous residual diagnostics, a regression output is just an elegant mathematical lie, skewed entirely by extreme anomalies. When diagnostics fail, we do not throw the model away. We engineer a structural correction. For non-linear errors, we apply Box-Cox power transformations to reshape the response variable and force alignment. To mitigate outliers, we utilize robust regression techniques like M-estimators. Instead of deleting anomalous data, these algorithms mathematically downweight their gravitational pull. We must also correct model bloat. Throwing too many variables into the equation generates collinearity, identified by a VIF score over 10, which creates extreme numerical instability. To solve bloat, we use stepwise model selection. We evaluate the model against penalty algorithms like AIC and BIC. These criteria strictly punish the model for unnecessary complexity, methodically dropping insignificant variables and forcing the equation back to its most elegant, simple form. As the statistician George Box noted, all models are wrong, but some are useful. The goal of statistical learning is not to perfectly replicate reality. It is to isolate the signal from the noise, building a meticulously encoded, mathematically sound abstraction that is robust enough to survive the future.